current, you will now need a larger device. Yes.
Okay.
So what happens in the subthreshold region? So subthreshold region also there is some current flowing, is it not?
Yes, sir.
Subthreshold region also there is some current flowing. So अभी तक जो हमने देखा super threshold region, that is above VT, we saw that okay, it remains quadratic for some time, then it goes linear. What happens in the subthreshold region? The subthreshold region, the current changes exponentially. You remember this equation? The diode current?
Yes, sir.
Yes.
And the slope that we have in this region is called as subthreshold slope, this S.
Sir. Hello.
Yes.
Sir, I mean, like in during this condition, sir, if VGS is less than VT, then there would be a depletion region, right? There won't be any kind of inversion layer such that ID flows. That's a doubt, sir. I mean.
So you tell me, can there be no flow of current in a depletion region?
Regarding to the equations and considering the equations, I think there shouldn't be any kind of
no, forget about equations. Again, see, अभी तो हमने देखा इतना सारा कि सारी equations हम घुमा देते हैं अलग-अलग तरह से मॉडल करने के लिए a silicon behavior, is it not?
Yes, sir.
So you should not learn it backwards.
Okay, so sir, my doubt is that
let us say there is a PN junction.
Okay.
Let us say there's a PN junction and you're applying two different voltages on the other side.
Between gate and body, or where, sir, exactly PN junction?
You tell me in a Mosfet where is a PN junction?
Sir, actually, if you talk about the current, then current flow, then we should talk about the source and source inversion layer and the drain, right, sir?
Inversion layer. Body. So when you made the source, you will form a depletion region?
Yes, sir. Yes, sir.
When you make a drain, you will form a depletion region?
Yes.
That was what we saw in the previous slide also, na? That these new depletion regions start to appear as soon as you made those source and drain?
Yes, sir.
So whenever there is this PN junction, so these are PN junctions, is it not?
Yes, sir, but they won't be evident as bodies at low voltage. I'm like, they are reverse biased, to be precise.
Yeah, but is there no reverse bias current? They're always reverse biased.
Yes, sir.
You do not ever want to have those PN junctions forward biased.
Yes, sir. Okay. Yes.
But there is a reverse bias current.
Okay. Okay, sir. I do understand that, sir. But I'm like, what is this exactly, sir? Current flow between source and drain, or drain and body?
It could be both. Over here, we're talking about subthreshold current means charge flow from source to drain.
Okay, sir. Okay.
But in reality, leakage will happen everywhere.
Okay, sir. Okay.
Because this slide is on subthreshold conduction. Over here, we are talking about current charge that would flow from source to the drain.
Okay, sir. Understood.
I know that there is a depletion region, a PN junction on the source. There is also a PN junction on the drain. And there is a depletion region in between them.
Yes, sir.
So that depletion region is all connected. So if some electrons enter into this depletion region, they will be at once pulled towards the drain. Is it not?
Yes, sir. That might happen. I'm like the minority charge carriers.
Yes. So that is what the subthreshold conduction is about. That even when you are not at VT, there is some band bending happening, there is some depletion region, and therefore there will be some flow of current.
Yes, sir. Understood.
Okay. Faisal?
I have a doubt from the previous slide of a short channel. The current, the current is decreased. Like, why is it decreasing? Current is charge flow per unit time. So in short channel, like charge तो उतना ही होगा ना सिलिकॉन में.
हाँ, but उसकी velocity कम हो गई ना. Velocity अब बढ़ नहीं सकती जितना आप चाहते थे. Due to velocity saturation.
Velocity saturation तो सर long channel में भी था ना.
लॉन्ग चैनल में लॉन्ग चैनल में वेलोसिटी सैचुरेशन तब था जब इलेक्ट्रिक फील्ड उतना पहुंचता, वो बहुत देर में पहुंचता. that you will probably not even observe.
Okay.
Velocity saturation is the behavior of silicon. So वो हमेशा ही था.
Yes,
But
sir.
electric fields were never so high that you would observe it on a long channel device.
So, like, is it like velocity saturation था? इसका velocity saturation V1 था, long channel का, उसका velocity saturation V2 था, और उसमें V1 is
No.
greater than V2. ऐसा नहीं है.
Velocity saturation is behavior of silicon.
Okay.
Velocity saturation is behavior of silicon. यहाँ पे channel
sir.
length की कोई बात नहीं है.
Yes, sir.
यहाँ पे खाली electric field की बात है.
Okay.
Okay.
Okay, sir. Okay.
When the electric field goes that high, velocity would saturate.
Yes, sir.
In long channel devices, electric field doesn't reach there
अच्छा वहाँ. Okay, okay, okay. Okay, sir. Now
because the length. What is electric field? It is delta V by L. The
Yes,
length
sir.
is large, so electric field is low.
Okay. Okay.
In short channel devices, length is reduced, so
Yes,
electric
sir.
field goes high.
Okay, sir.
Okay.
Yes, sir.
So, Meher, you have a question?
Yeah, so I really didn't understand this sub-threshold conduction part. I mean, how are we getting that exponential graph and then how it varies?
Okay, so it's not, again, we observe this on silicon, we realize it is exponential, and then we model it.
Okay. Because as Gagandeep said, it's like, it's almost like, you know, PN junction, right? But I'm confused as to where a PN junction will be formed because there's before VT, there's a depletion region, right? Between
Wait. Depletion region का मतलब क्या है?
that there are no charge
No.
carriers.
Where would a depletion region be formed?
So
Where there is N plus
right
type
under
and
the
this
gate.
is P. Is it
Yeah.
not? So this
Yeah,
is a PN junction, is it not?
Yes.
Similarly, there is a PN junction here.
Yeah. Okay.
And then depending on gate voltage, there is a depletion region here.
Yeah.
If this depletion region is very less, let us say that the gate voltage is such that this depletion region is very less, there will be very minuscule conduction of current. Because even if electrons enter here, they will
Right.
exit from here. There is a very large region where they could exit from
Okay.
into the body. Now you increase the gate voltage. Depletion region became large.
Right.
Now most electrons will move from here to here.
Okay. Okay.
And that relationship is exponential in nature. आप हल्का सा VGS increase करोगे, depletion region हल्का सा और बढ़ेगा, and huge surge of electrons moving from
Right.
source region to the drain region.
Okay. But so this is ID versus VGS, right? So this should be the slope should be pointing upwards, shouldn't it?
मतलब
Well, when you're
increasing VGS,
keeping VD fixed and you're increasing VGS, you're increasing the overdrive voltage. So I mean, in long channel devices, it grows in a quadratic manner, right?
yeah.
So here I'm assuming this is for a short channel device, is it not?
Yes.
So I mean, it has a very different behavior. Like first I mean, the slope is decreasing. How so? I mean,
Because initially the change of charge or change of current is exponential, then it goes quadratic, then velocity saturation happens, it becomes linear. The slope has to degrade.
okay. Okay, yeah. Sorry, I got confused with it. Fine.
ठीक तो है?
See.
You're saying the same thing.
Yeah.
So this is logarithmic axis, right?
Yes.
ID.
That is why exponential looks to be linear.
Yes, sir.
Rajneesh?
Sir, this leakage, sir, it will be completely dependent on VDS, no?
अभी तो हम देख रहे हैं VGS ग्राफ में it is dependent on exponentially.
नहीं sir, this substrate leakage, this thing will be completely dependent on VGS, no? Sir, whatever VDS, sir, not VGS, VDS.
So that is what I'm telling you. It is also dependent on VGS.
Sir, how, sir?
That is how, that is the behavior. Because the depletion region, so अभी जो एक photo बनाई थी यहाँ पे, there was this depletion region, there was this depletion region. If my
Yes.
VGS is negative, that is, I do not have any depletion layer,
Yes.
then there is no connection between these two. There will be no VD, no ID.
Okay. Yes.
As soon as I increase VGS, what happens? Depletion region starts to become there. So electron that enters into this depletion region rushes there.
Yes.
Earlier, there was no such path. So when there was no such path, there would be nothing. So VGS पे dependence होगा. If this VGS is low, this region through which electrons can move from here to here is lesser. Current would be lesser.
Yes.
So there is a dependence on VGS.
Yes. So basically, at in this graph, one thing, sir. So basically, we want low VT, no? Because more leakage will occur due to low VT, sir. According
So
to
we
this
want
graph.
more leakage.
No, we want less leakage. So that's
Yes.
why where VT should be near to this
Higher.
point.
Your VT should be as high as possible ताकि leakage कम हो जाए. So that when your gate is at 0, you have as low current as possible.
Yes, sir.
But
So
in advanced technologies, you will see that this is what happens.
okay. So ऊपर वाला मतलब वो practical है, sir.
Practical है
मतलब जो really होता है, sir, graph मतलब.
ये भी really होता है. But in advanced technologies, because you want speed and you want to lower the VDD of operation, you go to lower VTs. So the curve would become something like this.
Okay, sir.
Okay.
Yes.
Additionally, see, let us say this is the device. If I say that my subthreshold slope goes bad, what happens? If my subthreshold slope goes bad, then I will have lower subthreshold current. So we want a subthreshold slope such that within 60 millivolts, which is the limit of silicon, within 60 millivolts, you should be able to reduce current by 1 decade. So this should be 60 millivolts. Okay. But in reality, it is anywhere between 70 to 100. The lower it is, the better that technology is. But there are other reasons because of which it cannot really come to 60. 60 is a theoretical limit for silicon. Okay.
Sir, I'm
Yes.
sorry, but I'm still a bit confused. In the previous slide, can you show me the small length, small length modulation? I mean, small channel, yeah. So there it's first quadratic, then linear, and this is ID versus VGS, right? And then in the graph for subthreshold, the slope is decreasing.
Quadratic and then linear. So look at this. This is exponential axis. There's a logarithmic axis there.
Okay, this is logarithmic.
पढ़ो ना.
Right. Okay.
This is logarithmic axis and that was linear axis.
Right. Fine. Okay.
Okay.
Sir,
Yes.
sir, in the subthreshold, when you were discussing subthreshold, you said that when we were going towards like higher nodes, then we were getting the changes so that we were not basically reducing the subthreshold or the leakage currents basically. So like, does it mean that we cannot escape that kind of phenomena? Because you said that the graph was shifting upward, that where it was cutting this ID axis, the y axis, it is moving up. You showed that.
Yeah.
So
I showed something like this, that the slope is not good.
yeah, yes, sir. So sir, I mean, like, even if we are going towards that, if we reduce the VT, then also we cannot escape this kind of phenomena basically. somehow it just jumps back and we get the same kind of effect.
Yeah. So leakage is a very major issue in advanced technologies.
Okay. So earlier we used to think that if we reduce the VT, we would reduce the leakage, but it is not happening that way.
No. VT reduction would also always lead to increase in leakage.
So VT reduction would increase the leakage.
Yes. What does VT reduction mean? VT reduction means that I will shift this entire curve a little more on this side. Right?
Okay. I didn't think of any shifting terms. I was thinking like
Reducing
this.
VT means shifting it, na?
Okay, right.
So it means it will hit it at a higher current. So leakage would definitely increase as you decrease the VT.
Okay, so the more speed I'm going towards, then I'm getting the more leakage kind of phenomena.
Yes.
Okay, sir. Thank you, sir.
Okay. So this is in the same technology. If you reduce VT, this will happen. What I'm saying is, if the technology is bad, then even with the same VT, you can actually end up having higher leakage.
So this I cannot understand. That with this, even the same technology, what exactly?
This is a different technology. So a technology has a characteristic sub-threshold slope.
Okay.
If you change the technology, this slope would change.
Okay. So
I have same VT, but due to short channel effects, due to punch through, whatever reasons, due to various reasons, I will have a different slope.
So these different red curves are basically different technology nodes, right?
Yes.
And having the same VT kind of thing.
Technology nodes nahi kahenge. It could be 65 nanometer technology only, but one could be from TSMC, another one could be from Global Foundries, another one could be from Samsung.
Okay, so though they're having the same VT, but the sub-threshold characterization different. Okay.
So whenever you look at technology, you can not just look at VT kya hai. You also need to look at how is the leakage moving, because that gives you the sub-threshold slope ka estimate.
And so ideally we want that within this 60 kind of change, we want this 100.
Yeah, ideally we want 1 decade ka reduction ho jaye within 60 millivolts, because silicon usse better dikha nahi sakta hai.
Okay.
Excuse me,
Okay.
sir.
Yes.
So I still didn't get why we are having a quadratic behavior and then a linear behavior. Now, are we operating in saturation region in both?
Yeah. So what happens? Let us go back to the earlier curves. So IGS, this is VGS ID characteristic. Okay, for a given VDS.
In saturation, sir.
Yes.
Okay, sir.
अगर saturation नहीं होगा तो current anyway IDS की वजह से ही linear हो जाएगा ना?
Yes, sir.
है ना? So we are talking about VDS, which is saturation. VDS, which is greater than VGS minus VT. So in long channel devices, as you increased VGS, the behavior was quadratic. In short channel devices, it remains quadratic for a little while, but then it becomes linear.
Okay, sir. And so what was the reason for this?
One reason is velocity saturation, but there are other reasons also. But I don't want to go into those details, otherwise we will get digressed too much. That is what I'm noticing with this class, which is, I'm happy because you're learning more things, but then we need to progress in terms of syllabus also.
Okay, sir.
So you can use the reference book and you will be able to find out. Details are there also. So that is not the agenda of this class. Okay.
Okay, sir.
So I think it's already 1:20. We can close the class now. Any questions?
Yes, sir.
So I have one request to make. Can I?
Gagandeep had a question. Let's handle that question first.
Okay, sir.
Yeah.
Yes, sir. I was asking that, sir, in older technologies, when we were not going to very low voltages, at that point of time, this sub-threshold current would not really be something that we was worried about, right? I mean, when
Yeah, in older technologies, the VT was also very high, 0.7, 0.8 volt hota tha VT. So even if the slope was bad, the leakage current would be low. Additionally, older technologies, the total number of devices that you can put on silicon is also low, is also less. So total leakage never bothered us. In advanced technologies, as we are integrating more devices onto the same die, and each of those devices is also leaking more because of advanced technology nodes. Leakage is a major issue, or low power and portable devices, leakage is a major issue. So we have many schemes, as we will look at later in the course also, to reduce leakage. Leakage recovery is a special task that is done when you design chips. Okay.
Some kind of implants and all this.
Yeah, you will see that in VDS. Yes, Faisal, you wanted to say something?
Yes, sir. So it is about the quiz, a quiz for 2 lectures would be better. And in between them, your office hour will be good, like will clarify our doubt, then we'll move to quiz. Then it would be better. And if you're trying to have a quiz on Wednesday or Friday next week, like then we'll have one more lecture. Our doubts will not be clarified. And like,
So we'll have it at 8 p.m. on Monday. Don't worry.
yeah. Okay. Then it's okay.
8 p.m. on Monday is fine with everyone, I believe.
Sir,
Yes, Raghav?
sir, I had a question only regarding velocity saturation thing. So like I understood that because of the velocity saturation in the short channel, we are not able to achieve the kind of current which we were in the long channel. So, but the current, according to, as I also visualize, current depends upon the number of charge carriers, right? So even if I am getting the same amount of charge carriers, even at a very low kind of voltage, then the current, I should be able to achieve that kind of like peak, like that kind of like voltage current level. I mean, electric field
Is it just dependent on number of charge carriers or also on their velocity?
No, sir, it depends upon the velocity, but still, if I'm able to like achieve the kind of numbers, like in the terms of density, then I'm able, even if I'm getting them, like I'm achieving the velocity, higher velocity at a lower level, but I will be able to maintain that kind of current level.
Yeah, वो तो हमने अभी बात करी ना, Faisal. We said, Raghav, we said that if we increase the width of the device, we will be able to do it.
Okay, like the Gangdeep said, okay. So
yeah.
by increasing
the width of the device, you will have larger number of electrons available with you.
Okay. But then we don't want to increase the size.